Alright everybody, video on 6.6. This time we've got a few proportionality theorems and how we can use them. So, proportionality, again, we've been talking about that term throughout the whole chapter, is the idea that two ratios are equal to each other and sort of how you show that and, what the ramifications of having a situation like that are. So, starting right with it, we have the triangle proportionality theorem. And what this states is that if a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. So you just need a parallel line to the other side. So in this picture, that would be this side, and here's our line cutting through the other two sides. You do see here that it intersects both of those other sides. What we're going to have then is we're going to have these sides being split proportionally. So we'll talk about what that means coming up in a few examples. The converse to this, remember converse is when we sort of take the two parts and we switch them, is that if a line divides two sides of a triangle proportionally, then it is parallel to the third side. So if we knew, like, let's put a few variables here. Let's say that the length from here to here is x, and length from here to here is y, and length from here to here is a, and from here to here is b. If we were told that y over x equals b over a, then we would be able to say that this side was parallel to this segment that's cutting through it. Okay, so an example of this being used. Here we have two lines, triangle, and we have two lines, two parts that are parallel to each other. We can see that because of the arrows that they have. And remember, what the proportionality theorem says is that if we have a line that is parallel to a side, then it's splitting the two sides that it's cutting through, that parallel line right here, it's splitting the two sides that it's cutting through proportionally. So, if we want to find x up there, we're going to just have to set up a proportion. So, one proportion that we could set up is we could say, if we wanted to, that st over rs equals uq over rq. We can say this. So plugging in the values that we know, that would give us then 6 over 4 equals 9 over x. Using cross multiplication, 4 times 9 is 36, and 6 times x is 6x. If we divide both sides by 6, we'll get that x equals 6. So that would be the length of QR right there. Not too complicated, but there it is. All right, let's flip over to the other side of the note sheet then. Okay, so another example. On the shoe rack shown, AB, so this segment here, has a length of 33 centimeters. We're told that BC has a length of 27 centimeters. We're told that CD, so this part here, has a length of 44 centimeters. And we're told that DE has a length of 25 centimeters. Now we need to explain why we know the gray shelf. So here's the gray shelf sort of cutting, it's in the middle of the shape. Why that is not parallel to the floor. So why it's not completely even with the floor. It must be at a tilt or something. Well, we're going to figure out how we know that. Because we could use the converse of the proportionality theorem. All we need to do is see that these parts are proportional, or if they're not, and based on the results that we get from that, we'll be able to determine whether or not this line segment cutting through is parallel to the other one. So we just need to set up a few proportions. I'll start with CD and DE, and I'll set up 44 over 25. And it would probably be a good idea here to turn this into a decimal, so I'll just enter that into my calculator. 44 divided by 25 gives us 1.76. So I started with that top segment and went to the bottom. If this is proportional, I should be able to do the same thing with CA, and we'll get a similar result. So I had 44 over 25. Now I'm going to do 27 over 33, because I'm taking the top value divided by the bottom value. 27 divided by 33 gives us 0.81 repeating. Clearly that is not the same thing as 1.76. So since these two ratios were not the same, this gray shelf can't be parallel. It's not working out. We don't have lines that are proportional here, or ratios that are proportional. So the gray shelf is not parallel. We just use the converse of the proportionality theorem. So because these are different, it didn't work out. All right. So another proportionality theorem is down here with this picture. If three parallel lines intersect two transversals, remember transversals are lines that cut through other lines, then they divide the transversals, you guessed it, proportionally. So in this picture, we have our parallel lines, we have the two transversals, and they're telling us that UW over wy equals Vx over Xz. So you can see how it's sort of splitting it up, where this part here is proportional to this part, or in the same ratio as that part, and the same ratio applies for the matchup on the bottom in the same locations. So, using this in an example, find the value of x. Well, following the example, or the notes from above, we should be able to put dE over EF, 6 over 8, and have that be equal to the ones that match up this way in the same positions. So 6 matches up with x, and 8 matches up with 10. So we have this setup. 10 times 6 is 60, equals 8x. So we just have to divide both of these by 8. And you're going to get from that result that x equals 7.5. So that's the idea of the proportionality theorems. And that's actually the last section purely out of the book that we're going to have here for this chapter. But coming up, you're going to be learning about something called transformations, which are, it may take you a little while to get through because there's a lot of information there. But transformations are actually pretty interesting, and they do have lots of ramifications for things like art and building design and generally designing anything, because sometimes you want a shape, but you have to tweak it just a little bit, and transformations can give you ways to do so. So, see you at the next video for transformations.